Hi everyone, contest has likely started. It's 8-5 already. I haven't registered for the contest because I missed it. But I want to do good in this contest. I want to do good in this contest. I will register after 10 minutes because I missed it. But yeah, interactive graph. Seems nice problems. So let me read the first problem. Alex and Bob are given two integers P and Q and they are playing a game with these numbers. The players take turns with Alex going first. On the turn, a player can do one of two actions. Decrease P by 1. This action is possible if P greater than 0. Decrease Q by 1. Okay? A player can do one of that. Like they have two integers. They can either decrease P or Q. The game ends when P equals to 0 and Q equals to 1. Bob wins if at any point during the game the fraction P by Q is equal in value to the fraction 2 by 3. Otherwise, Alice wins. Given the initial values of P comma Q, determine who is the winner of the game. Yeah, so it's a nice problem. We have to just find a way, like if there is a way that Bob can get this fraction at some time, or we have to see if Alice can bring it to here. Okay, Q should be greater than 1. So eventually the game comes here because if people keep decreasing, eventually P becomes 0, eventually Q becomes 1, right? So how can we do this? Like, P, Q, okay? Both are greater than or equals to 1. If P by Q equals to 2 by 3, Bob wins already. Right. Else P will be 2k, Q will be some 3k. Right. If P by Q less than 2 by 3, I think Alice can keep reducing. So if P by Q less than 2 by 3, I think if what if Alice keep reducing P, what happens then? Here, if you reduce here, 1 by 2 has been reduced. Here, if the next guy reduces the other thing, 1 by 3 has been reduced because it's going more lesser. It will always stay, this value will always stay less than this value. Like P by Q will always be less than 2 by 3 because Alice can make sure by doing P minus minus. So if Alice will do P minus minus, even if Bob does Q minus minus, I think, see, the value, we want the proportionality to become 2 by 3. But if it is already less than that, and with respect to these values, like what is inside of 2 and what is inside of 3, Alice is reducing it even further. Like we want these inside of these values to be equal, right? 2k, 3k is what we want, but it's Alice can already reduce more than whatever Bob can reduce. Okay, what if P by Q greater than 2 by 3? What does that mean? P equals to 2Q and Q equals to... P should be even, right, for sure. It may not be very difficult, yeah. I can take time till 10 minutes, but that's wrong. I can invest my time on B, right? Yeah, I have to be quick. Some C, let's say, okay? At each move, because P by Q is bigger, Alice would wanna reduce. Finally, P by Q value is 0. Right, finally it is 0. Initially it is 2 by 3. Greater than 2 by 3. I think at some point it will definitely come to 2 by 3 if this is the case. Or it will come close to 2 by 3. Here Bob won already. First, it's already 2 by 3. If at any point, if it is like that, it is gone. So if it is greater than 2 by 3, what are they doing? Like one person can change this value by half. The other person can change this value by 1 by 3. So these are the only operations they have, right? And let this be a fraction, whatever the initial fraction is. 2 times initial value, okay? P0 minus half. They can do some halves here. 3 times initial value minus. They can do some 1 by 3s here. This is what they can do. And the value will become 0 after a while. Is it always possible to come here? We have to just think about that. So, can allies again play better here? Think of that. Can allies play better again? So, what do I mean by that is, whenever q equals to 3k plus 1, okay, because they are going minus 1 minus 1, whenever q becomes is about to approach a 3 multiple, okay, if q equals to 3k plus 1, does does if p is even, p minus minus, if p is odd, now there is an issue here. If p is odd, there are two cases here, okay? If p is odd, uh, if p equals to 2k plus 1, else, so we have two cases. If p not equals to 2k plus 1, he can safely do he can safely do p minus minus, because then what happens, p becomes, there is no way that he can do this and then get there. It will repeat whatever Bob does here. He can only change. If he does q, nothing will happen, because anyway p is not 2k plus 1. If Bob plays on P, we are again coming to the same loop here. Like we are again looking at P comma Q and we're trying to follow things. What if P equals to 2k plus 1? Can allies win here too? If P equals to 2k plus 1, allies has to do something. Allies has to reduce one of these things, right? If allies reduces this, Bob will win. If allies reduces this one, also then Bob will win. When we are at 3k plus 1, this is right. Whatever allies does, Bob will win. So if it is 2k plus 1 and if this is 3k plus 1, whatever allies does, Bob will win. So we know 2k, 3k or bad, 2k plus 1, 3k plus 1 or bad. Is there a way where allies can again win here? Like if whenever p is even, can he manipulate 3 reminder to be even? 0, 1, 2, 0, 1, 2, right? Here he cannot manipulate that to be even, because 1 minus minus is changing parity. This is also changing parity, but this is not changing parity. So in terms of odd reminders, if we can make it even, whenever q becomes this, he will make p even, let's say. Okay. Whenever q becomes this, can he make it even? So if q is this, before q becomes this, now I can register for the contest. Oh, many people have solved it. Why am I not able to solve? I'm overcomplicating it. I'm overcomplicating it. Maybe in other case, we can always get it. Maybe. Is there a way Bob can win? Let me think about that. Is there a way can Bob can win here always? So let's look at this even value 2k, and then we have this 3k, right? Mm, let's say this is always bigger, right? This is always bigger, and finally it goes to, and finally it goes to 2 by 3. Let's say Bob is always keeping this one bigger. Alliance will still reduce this one, right? So we are having this is being bigger. Alliance will try to reduce this, Bob will try to reduce this. So Alliance can reduce minus half here, Bob can reduce minus 1 by 3 here. If they keep on going, this value is bigger. Let's say Bob is trying to make this greater than or equals to 2 by 3. The first time, should I guess something? We have a fraction currently. Either minus 1 is happening. Will it definitely reach 2 by 3? May not be, right? I don't know. Maybe it reaches 2 by 3 always. Should I guess that? But guessing is too bad, right? If p by q less than 2 by 3, which is nothing but 3 times p less than or equals to 2 times q. Alice can win. Else if 3 times p, else Bob will win. This is a guess. Not good at guesses for sure. Oh, even here, Alice can win. If PYQ is greater also, if it is much greater also, Alice can win, it seems. Because Alice can keep reducing this one, and then it will always be greater than, it will always be 1. In this case, it will always be equal, right? Wait a minute. If it is greater than or equals to, okay, if this is greater than or equals to, then also Alice can win. Or if P greater than or equals to Q, Alice can always keep. So we finally want P, P minus Q is greater than or equals to, sorry, Q minus P is greater than or equals to K, right? If you can always keep Q smaller, even then Alice will win. So if Alice does Q minus 1, also here Alice can win. Else, if, which is nothing, if Q minus P is greater than or equals to K, let's think about that case. If Q minus P greater than or equals to K, whatever Alice does, Bob does the opposite, let's say, and this value will be greater than or equals to 1 always. Okay? Not able to get anything. But I cannot submit this shit. How can I prove it if it is true? In all other cases, can Bob win? If this is greater than or equals to, let's say Bob is doing the opposite one. Okay? And there reaches a point where there reaches a point where if Bob is keep on doing it, there reaches a point where P becomes 2. And now let Q minus P equals to K initially. And then they have done Q minus C, P minus C. Okay? Whatever Alice has done, Bob has done minus same value. What happens to this value? 3 times P minus 2 times Q. 3 times P minus c minus 2 times q. How is this value reducing in this process? If you see this value, how is it changing is, so initially p by q is greater than 2 by 3, right? In our leftover case. So initially this is greater than 0. How is this value changing now? This value is becoming minus c. If you see, this value is becoming minus c. As c increases, this will definitely come to a place where it becomes 0. So we have proved it perfectly. Now this works. Wait a minute. 3p minus 2q greater than 0. But this should happen before q becomes 0 or p becomes 1. Right? But each one of them has this power, right? Each one of them has this power to do this thing. Like if Bob does, he can do the other thing and maintain this difference, and this value will reduce by at max 1. Like each of them has a power to reduce this value by at max 1 by choosing the opposite value. So I think this solves the problem for sure. Like each of them has that power. So if 3 times p minus 2 times q is less than or equals to minimum of p comma q minus 1. So these many moves you can do without losing. But is this the answer? This value will finally become, q will become 1, p will become 0. The value will finally become minus 2, right? And if whatever Alex chooses, if Bob chooses the opposite one, what happens is it reduces by minus 1. This value will reduce by minus 1. Finally, it's becoming minus 2. So it must go to 0. But then why is this failing? What am I doing? So I'm very clear now. This value will always become minus 1, minus 1, minus 1, and finally it's becoming minus 2. So it will become 0 in between for sure. It cannot become 0 only when after he makes a move, if he cannot make a move, if he can choose the opposite one. Oh, if he cannot choose the opposite one, then it's gone, right? That's where it ends. This logic holds true if he can choose the opposite one, else it will fail. I get it now. I'm taking too much time on this. Why? Bob wants to reduce this value. Okay, so because it's initially to 0, and it's initially it is, you can always keep it odd or even. Those things have been removed, right? Because so is this the tight condition then? Because if this is less than or equals to this, Alex can always go for increasing the value. He can always do q minus q minus q minus, and he must be doing p minus p minus p minus. And after some time, this will be gone, and Alex will win. 3 times p minus 2 times q greater than p minus 1 comma q minus 2. So if they make p comma q minus 1, if they make these many number of moves, Alex will win. But in each move, Bob's best try. Even after this, there may be a case where Alex can win. Why am I not able to solve this one? Why am I complicating it? Else, whatever allies chooses, Bob will choose the opposite one and keep reducing this value by minus 1, minus 1, minus 1, minus 1. And what is the else condition? 3p minus 2q less than or equals to min of p comma q minus 1. No, when this value reduces by 1, only one of them will reduce. Alliance will increase this. Let's say Bob must go for this. This is too much. In the array, we call a pair of integers I indices I comma j beautiful if the following condition holds. Count the number of beautiful pairs in array. This is more direct problem. Let me try this one before getting stuck on A. We want number of beautiful pairs, count of beautiful pairs, right? Ai aj equals to I times j. Ai comma aj values are less than or equals to 1 u9. So how do we count these pairs? What can we fix first? What can we not fix? J minus I less than or equals to 2e5. So this should be the main thing. That's it. Maybe even when it is equal, because allies can go first, right? Oops, oops, oopsie. Should I just not give this contest? Is that the best for me now? Think about it, guys. Nah, that's too much. That's too much. I can solve problems. I have 2 hours and it's negative rating or negative rating is fun, but I can solve the problems. Less than or equals to 2e5, right? So both the values should be less than or equals to 2e5. So either value ai times aj less than or equals to 2e5 means either of them will be less than or equals to root of 2e5, right? So one of them is less than or equals to root 2e5. Okay. And if you fix that value, okay, ai is fixed, let's say. We are assuming where ai is less than or equals to root of 2e5. We are brute forcing it now. So AI equals to k, let's say. And now we have k times aj equals to j minus I. AI's value has been fixed. So we have to go for j minus k times aj equals to I. Let's say if you're fixing AI's value, where AI's value is less than or equals to k, and then we'll go over all such values, okay? For each of these values, we want number of indices j such that this equals to I. So what do we do? See, both the values should be less than or equals to 2 if I. This 29 is waste. You want just count off the things where for some I you want just count off these things. So for k, you can easily do this if you're brute forcing k, because you will find these values for all j's. See, j equals to I cannot happen, j less than I cannot happen. For all AI where if AI less than or equals to root k, you can find this value for all j's, and then if it is between 1 and n, you will update the frequency, and then for I, if how many j's are coming. So this is done. If AI is greater than root n, now we have to worry. Then aj will be less than root n. Okay, when both are less, that's a different case, but now we have to handle the different cases where AI is greater and aj is smaller. We have a problem when both of them are smaller. Or here we have to make sure that AI is greater than root n, and then we have to count these things, right? So we'll do the same thing here. When aj is less than or equals to this, we'll do the same thing, but we make sure that AI is greater than root n, okay? When aj is less than or equals to n, right? So what do? We count the same things in an opposite way. Uh, Let aj equals to k, and we have ai times k equals to j minus I. So ai times k minus I equals to j. We will count these things, and then for each j, we'll see there are how for each j, we'll try to see how many AIs are there whose value is i's are there whose value is greater than this. Only then we will add that. So it is done. So int n seen n int rn equals to 0 while rn times rn less than or equals to n rn plus plus. Okay, now we have root n. Now what will I do? So this was much easier than a for me, right? I mean, b is not that difficult problem anyway, but this was much easier. So we're brute forcing AI. What will I do? We're brute forcing AI, and then we have to count these frequencies for all j. So we have frequency. We're brute forcing AI for int j equals to 0, j less than n, j plus plus. What's the value I want? J minus k times aj. If frequency of val less than, what about 1 based and 0 based index? Is it fine? Yeah, that should be fine. Now we have these values, right? We want number of j for each k. For each k, now we want, for each I we want number of such j's. So what do? We want this value to be equal to I, right? So now the answer is, for int I equals to 0, I less than n I plus plus, we want answer plus equals to frequency of frequency of I. If a of I equals to k, that's done. Force aj. Almost the same thing, exactly the same thing. But we are brute forcing, we are trying to find i's here. And then the values ai times k minus I. But we have one more condition here. And a of I is greater than root n. We have this condition, like if ai is less than root n, we cannot do that. We have to count such things where a of I is greater than root n, and this happens, then that's a pair where aj is less than or equals to that, right? So I think this is the answer. Am I double counting something? I plus ai times k. Passed. So we have solved this problem easily. It's a brute force problem, easy brute force problem. Now let's go for C1. This is the simplest version of the problem. The difference between the versions is that in this version you can ask no more than 32 times n plus m questions, and n less than or equals to 50. You can hack only if you solve both the versions. Here, n less than or equals to 30, and you can ask no more than just n plus m questions. Okay, it's a nice problem. All interactive problems are nice problems, right? So let's try. I'm not getting negative rating. I'll solve this one. I'll solve the other one. I'll solve the A2 after coming back. The jury has thought of a directed acyclic graph without loops or edges, which has n vertices and m edges. So there is a directed acyclic graph without loops and multiple edges. There are no loops. There are no multiple edges. Acyclic directed with n vertices and m edges. Your task is to determine which edges are in this graph. To do this, you can ask following questions of the form. So we have a topological ordering too, and then you want what all pairs are having edges. What does the kth path look like in the lexicographically sorted list of all paths in the graph? Lexicographically sorted paths of a path in the graph is a sequence of vertices. This one, such that I less than L there exists an edge. So you have to just logically work on this. Like, okay, if you can get this sequence, how can you find that? If you can get logically lexicographically sorted list, kth path look like? The path in the graph is a sequence of vertices where all of them have an edges. Your task is to accomplish this by no more than 32 times n plus m questions. Lexicographically increasing paths, right? Lexicographically increasing path. So let's say you have this path, okay? You will get those paths. Let's say you have all the paths here, from the smallest path to all the paths. Okay, what is a path? Even a single vertex is a path, right? Yeah, even a single vertex is a path. So you have these paths, you have these lexicographically increasing paths. How can you get useful information always? How can you query less? How can you query any two times n plus 1? And then you have a way to query n plus m. Here you can do 32 times n plus m. What are all the number of paths? Total number of paths is total number of paths. Here is n is less than or equal here n is less than or equals to 30. Total number of paths is 2 power m. Total number of paths is 2 power 15 times n factorial. So you have this topological ordering, right? In topological ordering, at max, the total number of moves is 2 power 15 because once you choose a subset, the ordering is fixed already, so they will have edges. So this is the number of edges that are possible, 2 power 15 number of edges. Okay, we have to solve easy version first to help ourselves. And once you, how can you know there is an edge? How can you know there is an edge? The only way to know is if after this O of n plus m, right? 32 times. How can you progress from one vertex? Let's say you're taking a vertex, you can find where this one starts, right? You can find where this vertex starts, where the paths from this vertex starts, because they'll start somewhere. If you do binary search, you can find where this vertex starts. Okay, if the first value is smaller or larger. So now you have k where this vertex starts. Now can I find all these things? You can do binary searches to find all these things. So this case is very simple. C1 is very simple. You will try to see the next value now, and then once you get this one, you will try to see the next value, and then you can do again binary search. You can do again binary search. You can do again binary search until the next value is this. Again the binary search until the next value is this. Binary search until the next value is this. Paths that are starting from here. Okay, and then you have this one. So for a vertex, you can do vertex plus. So here you have done binary searches which are less than or equals to 32, because total number of edges itself is 2 power 15, right? And for each of them, for each binary search, you are able to resolve one value, resolve one value, resolve one value, resolve one edge, resolve one edge, resolve one edge, resolve one edge. So yeah, you're great here. And once after this, oh wait a minute, yeah, you have this value. You also have, when you find the next one, after this one ends, when you see the next one, that might be outside, that might be outside outside this itself. For that you have to check the first value and then the second value. Okay, so it's a simple implementation problem. Why are people not solving this one? Yeah, people will solve this one. It's a simple problem, right? So we will make our implementation clear. First we'll find this value for each u, and then we'll try to see the next one. Initially it will be just u, and then it will be u some vertex v1, u some vertex v2, up to so on, and then nothing. What happens if we query something outside? We get q equals to 0. Okay, yeah, if it doesn't exist, or if it exists and value not equals to 1, we stop. We have these things. First we'll binary search for u. Yeah, this is easy. C1 is easy. I can code C1 quick. How does C1 help us solve C2 is the bigger question now. They have to follow similar pattern. They cannot be entirely different idea. This is too direct compared to A, for me at least. Too direct. We have D, even E2. Even E2 are easier. We'll do binary search. Paths less than this, paths greater than or equals to this. Okay. QE30 is the maximum worst case for both the problems. Let me just do this. Okay. If Q not equals to 0 and let's also get path. Now right equals to U. Like at right you have V and nothing else. So right plus 1 you have to go to for you can start from right plus 1 now. Okay? So int left equals to okay. Temp L equals to left, temp R equals to right, let's say. So now we can keep left equals to right because this doesn't have that. And temp R you can keep right you can keep the same big value 2e30 plus 1. Okay. Now we'll keep increasing left here. Okay, you have this space from here to here. You have this space from here to here. Right. While true, what do? We'll check left plus 1, let's say. And then you'll get the path. Okay. If q equals to 0 or if q not equals to 0. So when do we continue? If q not equals to 0 and path of 0 equals to v, only this case we will continue, right? So if this doesn't happen, break. We are done. But if this is happening, you want how far the same value goes. Okay? Int u equals to path of 2, 1. This will exist for sure because all these are two length paths, right? So now you have u and then you have to do this thing again. Hmm, I'll use L comma R now. L equals to left, right equals to 2e30 plus 1, while left not equals to right. See, it's about number of paths that start from this vertex u. If you have that already, you can just skip to there and then you can directly query that. Is that C2? It's like after u, it's just number of paths that start from that vertex, right? All of them will just be there. And if you know that value already, this shit is done. This shit is done. Done. I think C2 itself is done. Okay, it's not done. Let me just code this one and then I'll try to think about the other one. If q not equals to 0 and path of 0 equals to v and path of 1 equals to u, then left equals to mid, else r equals to mid. Here we queried L plus 1. Here we started from L. We could have started from L plus 1 too. Anything works. Here itself you can add adj of v dot pushback of u has been discovered and then u has been traversed and then left should be L. And then we'll go to L plus 1. Let me just submit this. What the fuck? Why is it asking one again? Why is it asking one again? Left equals to zero, let's say. Wait, this is too big. We want 2 power 30, which is 29. Let me just do one. Okay, for this 32 is enough. 15 is enough. Because n is 15, right? For each vertex, we are doing first one thing. Okay? And then we are doing. So this L is definitely greater than this left. Because. Wait a minute. Have VU. And then not that. Why? Why should this fail? So now it is asking about 2. What is the path that 2 is 1, 2? Now it is asking at 17, which is definitely bigger. So we are trying to query for 1 comma 2, which is still 4. So after that we can keep 0. But now we have to keep the actual path 1 to 4, which is 3, 1, 2, 4. Now it's asking about 4. To say 3, 1, 2, 5. Now it's asking about 4 again. Wait, why do you have mid plus 1 here? Okay, that's an error. But now for C2, I think it's almost done. It's almost the same one. For C2, fun of V can give you number of paths from V and its adjoint of V. Let's say that's what fun of V does. Let's say now you can start from fun of 1. Like you will get you can try asking for fun of 1. Okay, how would you get that? How do you begin? See, how do you know the starting value of this one? That's the only question, right? How would you know the starting value? Continuity of n plus m. There is something to it that will let you know the start. If you know the starting positions of one, if you know the starting position, you can do this. Wait, wait. You don't need anything. You don't need anything. You don't need anything. You don't need starting posts. Instead, what you know is you need a pause value where you know smaller values v start. You know some smaller value and then v start. You need that index. That's all you need. If you know this, some smaller values and then v, that's all you need. Like some smaller values and then v is there and then n, nothing is there. And if you know this one's position, you can find it, because if you know this one's position, you will always go for, you can know the other one's positions by trying to query for the next one. So that's it. With this one, you know how many to ignore. Okay, how many to ignore you have. Okay, how many to ignore, how many to ignore, which is nothing but the size of this one. Okay, or where this one starts, where this one starts. Okay, you have where this one starts and a position. You have a position where this one starts. This is done. What will fun give you? It will give you the number of positions and it will automatically add edges too. Okay, I'll use V. You have V, you have some position, you have some IDX. Okay, in the path from where the this character V starts, you have this IDX. If you have these three, you can ideally find everything. So you have this position thing, okay, in the fun. You will only explore everything once because once you find its value, you won't explore once. You will be visiting many different states, but you won't explore them all. You'll only explore everything once, so that should be fine. So now what do? You get U, let's say, okay? Again. So you have a position now. Let's say you're not just index, I think you also want the prefix to verify this check, okay? If Q is less than, so we don't have this prefix. We started at C. Pos equals to pref plus V and nothing else. So we are trying to see if pref plus V something else is there or not. So we are trying to see plus one. If this doesn't match, that is it's something else, right? Okay, now it is greater than or equals to. For int I equals to 0, I less than ref dot size of I plus plus if ref of I not equals to path of I written. So now it is matching. So now you can get u equals to path of ref dot size of. Okay, because I have added this to the bref. I have added v to the bref here. Now what? You have v to the bref already. Now you have u. You want size of u so that you can skip that u. For int, yeah, you just want size of u. You just do fun of u, comma. You need a position from u, right? So you have this I. From here, this will start, and you have to ref dot pushback of u2 now. So now from here, oh, you need not do this because you can just go there, and then you have that. Now what should you do? You have to move I. I is the position where this one starts, and now you have how many things here, and then you have to do that many plus. I plus equals to memo of u, and then you'll go to the next one, and then you will check the same thing. If it fails, it fails, else you have this answer. Return. So you have initial position, you have final I, which would be here. Initial position is there. Return memo of v equals to I minus pos. So now you have to come here, and then you have to start from v equals to 1. Okay, and then you know initial position, right? From where 1 will start. So what do? Pos plus equals to fun of 1 comma pos comma pref empty. That's it. And then what will happen? We'll have v equals to 2. You might have added home already passed them, so it's again empty, and then it's done. So now the problem is done. And now where have you discovered an edge? You have discovered an edge when you form this u. So this is a very direct problem, but it has some complexity of recursive relations. Not even compelling. I should not be adding this. If I am adding that, I should pop it too. And like this coming back. Fuck it. try this. It's asking me what is second path. If I do 1 and 2, it's asking me what is third path. I'll do 1 and 2 and 4. Oops. It's asking me what is second path. I'll do 2, 1 and 2. Asking me what is third path. I'll do 3, 1, 2, 4. Asking me what is fourth path. I'll do 3 and then I'll do 1, 2, 5. It's asking me what is fifth path. I'll do 1, 3. Asking me second path. I'll do 2, 1, 2. Asking me what is third path. I'll do 3, 1, 2, 4. Fourth path. 3, 1, 2, 5. Fifth path is 1 and 3. So it is 2, 1, 3. Wait, why is it asking me fifth path again? This should be bad, right? This should not have happened somehow. So after this, okay, it found 2 and then let's say it's asking somehow. 2 was done and now it's asking to find if there is something after this. So it is 2, 1, 3. And then it's asking me 5 again. Why this time? 2, 1, 3. 2, 1, 3. And it's asking me 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 9. Seems it's working fine. 2, 2, 4. Asking me 12. 1, 12. 2, 3, 4. What the fuck? What the fuck is this? Is this correct? Why is it adding? Why is it adding? They both are not equal, right? Ref not equals to path. Should be, oh, programming. I forgot. I forgot programming. I guess asking AI to code. I think I forgot programming. I forgot programming. What was that error? What was that error? I have to break entirely, right? Not just that for loop. How long did I take for that? Long, quite a bit. I I am not able to break. I'm not able to break through a loop properly. I'm not able to break through two loops properly. Shit, that was trash. So now, what problem should I go for? Can I solve a problem in 1 hour? Seems difficult, right? But yeah, D seems the easiest one now. But let me try E2, even two. D has higher source somehow. Given a string S of even length consisting of opening, closing, open square, close square, which are brackets of two round and square. We call a string T beautiful if it satisfies two conditions simultaneously. All the subsequence of all round bracket comes forms a correct bracket sequence. All square bracket forms correct bracket sequence. Okay, we have two subsequences. All of them should form correct bracket sequence. Mm, you would like to turn S into a beautiful string. For this, you can change the characters in one operation. You can choose a position I such that I one less than or equals to I less than or equals to and change the character Si to any round or square bracket. What the? Oh, okay. Okay, nice problem. You can the operation is very powerful. You can change it to anything, and still you want. I can write some necessary things. Only constraints is the difference. And now the question is, how can you split one thing into substrings of other string where concatenation of substrings of other things where each of them differs at most once? Can you say the more the length, it is better? Let's say for P, the more length, let's say the last substring, the longer it is it better? Because you can always chop off some string that you're choosing, right? So the longer it is better, I guess, because you can always do lesser things. So the longer the shorter the string is better. The longer the last one, that's better. So is it just finding the longest length that differs at most once, and then it is just DP? So how do you find that longest length that differs at most once, and that matches with this? P. The longer this, that's better because the sh- the sh- leaving the shorter here, you can always erase these things from the substrings that you're choosing. So it is an increasing function with respect to length. So this longer is better. So now how do you get this longer? Like you want this string to be here somewhere, the longest such thing with one differing you want. Okay, even that is simple. Let's say this is not differing. This can be hash is one thing. So now the value is longest length where this is same and occurs in subtree. Okay, or this is not the longest differing one. Longest differing one is here. You can find that with the I minus one's value. What is the length? And then it's done. You have two possible values. So now all you need is what is the longest thing starting from here? That is a substring of this. That's all you need. Longest thing starting from here. That is a substring of this. Longest suffix. That is a substring of some other thing. I cannot ask AI, I guess. So this is the problem now. Longest suffix that has occurred somewhere here. That has occurred somewhere here. As a substring. Let's think about that. Can I do like pi somehow? You have some s and then you have some p here. Okay, longest string that has occurred somewhere. For this character, you have this length here. You can binary search on this length, I guess. So let's say you're binary searching on this length, and then now you have this substring. Does this occur somewhere here? As a substring is what you need, right? Does this occur as a substring is what you need. And if you're binary searching, you have this length. Let that be hash value, some hash value. Now you have to find if that hash is too different, if that hash exists somewhere here, if this substring exists somewhere here. Can you use some routine algorithm for this somehow? And routine. If this substring exists here, if this length exists here, let's split this into routine blocks, okay? Now we want this routine chain to be present somewhere here. Let's say you have m, okay? And then you have this routine, you have m, and then you have these routine blocks of some size, fixed size s, and then you have split everything into routine size blocks somehow, okay? Like everywhere starting you have this routine block, okay? For I you have this routine block. For something smaller, maybe let's just say you have that block itself. Okay, now you have these blocks of things that you care about. You have this O of m, care about blocks of sizes, okay? Let's store all these things somewhere in a map. You have these blocks of sizes that you care about. Now you can hash them and then store somewhere. So now you are here. When you are here in n, you will try to find for these specific blocks of m blocks, for these specific blocks you'll try to find what's the longest length chain that ends with this thing, okay? And for these blocks, what's the longest chain that fits? Let's define like this. What's the longest chain that so S should fit into some chain, some longest chain of blocks. Nah, 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 nah. What the fuck is this? You just have to check quickly. You just have to check quickly if This suffix is longest string of somewhere. Longest suffix that is this. My understanding was wrong. My recurrence is also wrong. This is much more complex. I mean, it may not be complex, but it may use original ideas from suffix automation, maybe. May not be too, but yeah, I'll try this one. This is having higher chance of me solving. Or I can just pause here. Should I try A? Oh, that's passing. That's it, guys. I'm ending. I cannot do B or E2. I will go and do my work, company's work.